Hello, everyone. Um, we have surpassed 100 participants, so let's begin. Um, so, um, Hello again. This is the fourth webinar in UNICEF's webinar series on data collection, which is organized by the Data and Analytics section at UNICEF headquarters. I'm Attila Hancıoğlu, Chief of the Data Collection Unit in the Data and Analytics section. Our webinar today is on non-response and waiting issues in telephone surveys by Raphael Nishimura. We continue the topic from last week, which was on coverage and sampling issues, again in telephone surveys. For those of you who may not have attended last week's webinar, Raphael is the Director of Sampling Operations in the Survey Research Operations of the Survey Research Center at the Institute of Social Research, University of Michigan. He has been working on sampling and survey statistics for over 10 years, holds a PhD in survey methodology from the University of Michigan, and a bachelor's degree in statistics from the University of Sao Paulo. His main research interests include sampling methods, survey non-response, and adaptive responsive designs. Raphael is also the director of the sampling program for survey statisticians of the Summer Institute for Survey Research Techniques, University of Michigan. Let me remind you that recordings of all of the webinars are posted on the SharePoint site. You can find the link in the emails you received, and we have started recording this webinar as well, and it will be posted to the same site tomorrow. We will aim to finish the webinar in 1.5 hours, including Q&A. And throughout the webinar, please remain muted, but please write your questions in the chat box. I will be reading the questions in the chat box and will direct them in groups to Raphael during the Q&A. So Raphael, please share your screen. The floor is all yours.
Thank you again, Attila. Can you see my screen?
Yes.
And can you see me?
We can see you too.
Okay, great. Thank you. Thank you again, Attila, for the introduction. Good morning, good afternoon, good evening to everyone. It's once again a pleasure to be here, to be talking a little bit more about telephone surveys. And this time I'm going to talk about a little bit about non-response and a little bit more about waiting. Today's presentation is a little bit longer than last week. So I'm going to, try to go a little bit quicker. And maybe if you missed something, apparently the recording's going to be available. So you might be able to watch it later, or if you want to take a look a little bit closer to certain slides, I think that the slides are also going to be available later. That's right. Okay, good. And there's going to be on this presentation much more mathematical formulae than last week, but I'm going to try to not focus so much on those. But for those who are interested in, like, are more mathy savvy or more statistics savvy and want to take a look at those, you can also look at those later. Anyhow, so starting with non-response, as probably a lot of you know, it's very important during data collection to have a final disposition code or outcome code to every simple element, because with those codes, those disposition or outcome codes, you can calculate things like outcome rates, like contact rate, response rates, cooperation rates. You can also use those to monitor and evaluate data collection quality. And as we're going to see later, they can be used to calculate weights or non-response rates. So I'm going to just go through here some very brief terminology, and also how to compute some of those rates. Not going to talk here specifically about like response rates in telephone surveys, because that varies from country to country, from even like within country. the topic of the survey, what are the survey protocols. So like it's, I know that a lot of you have like questions like, okay, what are typically response rates in telephone surveys? Are they, what I can say is that they are typically lower than face-to-face surveys, right? Like that's like something that we know in general, but like what is the typical telephone survey response rate? It's a little bit hard to answer without like the proper context. So I'm going to give here just a more general view of like how to track non-response, how to try to account for that. I'm not going to get in particular of like what are typical response rates in telephone surveys and things like that. So anyhow, as many of you know, what we would like to do when we are tracking these disposition outcomes, what happens to the contact attempts when you go into the field or during data collection, is we try to group them especially for response rate calculation, like for outcome calculations, into these 4 large groups, like whether a contact attempt led to an interview, whether there was a completed or partial interview, whether the case, we know that the case that we contacted was an eligible case for a survey, but for some reason we didn't get an interview, whether because it was a refusal, a non-contact, or for some other reasons. Or it could be that we know that that case is not eligible, is just not part of our target population. Whether again, they are not a housing unit, if you're talking about household surveys, or they're vacant housing units, or there are no eligible respondents. But there's also the case of certain sample cases that we just don't know whether they're eligible or not, what we call unknown eligibility. That's mostly because we're never able to contact anyone in the household to determine the eligibility of that household. Okay, so these are the 4 large groups that we typically want to keep track of for every simple case in our survey. But these different disposition codes, right? Like these 4 groups are in general, like pretty. They're pretty general in the sense of like, regardless of the mode of data collection, the type of survey, you're going to be able to classify most of the sample cases in those 4 groups. But the specific outcome or disposition code can vary by mode, especially the unknown eligibility cases, right? So, for example, on face-to-face surveys, if there is no one at home, if you now go to their house, knock on the door, and nobody ever answers, that's a typical case of unknown eligibility. But with telephone surveys, the focus of this of today's topic, there are different there are different situations that like you might not be able to determine eligibility. What if you call a number several times and nobody answers? You don't know if it's because that number just is not connected to a housing unit, or because it's connected, but for some reason nobody ever picked up the phone. Same thing a little bit with voicemails, right? Sometimes depending on the voicemail that you hear, you can't really determine whether that number belongs to a person, or maybe could belong to a business, or it's just like a automatic voicemail that that number doesn't actually belong to anyone, depending again from country to country how these things work. Mail and web, there are also different reasons why you would not be able to determine the eligibility. But anyhow, for different modes of data collection, you have different schemes of outcome and disposition codes. And I'm going to show that in the next few slides. So as I said, very important to collect these disposition results for every sample case. And then recategorize these more like detailed disposition codes into this like 4 large groups: eligible respondents, eligible non-respondents, ineligible, and cases that you don't know the eligibility. So here's just an example of one survey here in Michigan, or a disposition code that we use here in our surveys in Michigan, in which here you have like the more detailed disposition code. And based on like there are some crosswalks, and I'll show in the next slide one from the American Association for the Public Opinion Research that maps this more detailed disposition code into this 4 larger groups of final disposition code: eligible respondents, non-respondents, ineligible, and unknown eligibility. So this is just here an example. So a lot of the information about like how to categorize this outcome rate, these outcome codes or disposition codes, and also how to calculate outcome rates like response rates, cooperation rates, refusal rates. You can find on this page here, I left here the link of the American Association for Public Opinion Research. They have a very good report. They update that report from time to time. Like the last update was 2016. There's a link here. No, not a link. Like if you go to this link here and go to this other link, you're gonna find a PDF for this report. And they also have an Excel spreadsheet to calculate like response rates and other outcome rates. Very helpful. And so I'm just showing this because to show here on my next slide that how disposition codes can vary by mode, right? So here are 3 tables that you can find on that report that I was just referring to, where you see that I know that it's very small, so probably a lot of you cannot quite read here, but I promise if you go to that report, you're gonna find these tables at the end of the document. But you see here, like this first table is detailed disposition code. Again, categorizing each detailed disposition code into those 4 large groups for an RDD telephone survey. The second table here is for in-person household surveys, and this third table here is for mail surveys. And they have, I think, at least another 2 tables. There's another one for mail surveys. Then there's another one for web surveys. So this is very helpful in order to track how your sample has been, how to monitor how your sample has been performing, and at the end to compute those outcome rates. So speaking of computing those outcome rates, right? There are different also ways to compute response rates. And like on this report from APOR, they also provide these different formulas to compute response rates. I'm not going to go here in the interest of time through the details of each one of the 6 different formulas. Their differences, by the way, are very minor. The difference between this left-hand side and the right-hand side for each row is just that in the numerator, when you compute the response rate, you either include only the completed interviews, or you can include both the completed interviews, this I, and the partial interviews, this P. And the difference here around between the rows is just how you treat those cases that you don't know they are eligible, whether they are eligible or not. So like this response rate 1 and 2 treat those cases that you don't know if they're eligible or not as assuming that they are all eligible. So whether like if you were never able to contact anyone on that household, for example, to determine whether that household is eligible or not, you're going to treat those cases as eligible on this response rate 1 and 2. It's a very conservative response rate. You're going to have in general response rate, you're going to have a calculated response rate, probably much lower than the other 2. The other 4, sorry. This response rate 5 and 6 assumes that all of those cases that you don't know the eligibility are ineligible. So these are a more liberal response rate, or not as conservative, in the sense that you're going to have a calculated higher response rate if you use these 2. And this 3 and 4 here is kind of like in between. It tries to estimate what proportion of those cases that you don't know the eligibility would be eligible, and account for that. And I'm going to actually mention that in a second. And actually what I said on the previous slides, what is here, right? Response rate should reflect the number of units that responded out of the total number of eligible units. But you may not know the eligibility status for all the cases in your sample. So one way, there are a couple of ways to deal with that. One is to set a certain eligibility rate to certain extreme values, right? Like you can assume that everyone is eligible. So you would assume that like an estimated proportion of cases that are eligible, this E here is equal to 1, and that's the case for, as I mentioned before, response rate 1 and 2. You can assume that none of those cases are eligible, like this estimated response rate equal to 0. That's the case of response rate 5 and 6. And the case of the response rate 3 and 4 tries to estimate empirically this estimate E, the proportion of cases that would be eligible among those cases that you don't know the eligibility. And the way it does is very simple. It takes, it counts all the cases that you know the eligibility status, that meaning the eligible cases and the ineligible cases, right? Like that's the denominator here of this E, and takes here on the numerator only the cases that are eligible, right? So it's a very simple estimate for the eligibility rate. And you use this eligibility rate on the computation for response rates 3 and 4. It's a more like, I think, in between response rate you're gonna get compared to like this response rate 1 and 2 and 5 and 6, and more empirical as well. So that's the one that we usually try to suggest to most of the cases. And again, like here's the source for, and there is actually another document at that same APOR website where you can find different also methods to calculate this eligibility rate. I left here as a source. Okay, so this is all I wanted to say about non-response. Not really so much about non-response than like actually tracking non-response and how to compute this outcome rates. But this is going to be important later on when we talk about non-response weights. So now on my presentation, I'm getting here at the part where I talk about survey weights, so weighting. And again, today there is just so much I can do within like an hour or less than an hour, right? Like to talk about weighting. Like I usually teach a workshop during the summer here at university that I spend an entire week, 5 days in a week, 3 hours per day talking about weighting, right? So I'm going to try to give a very general idea of like how survey weighting works. I'm going to try to focus a little bit on the telephone survey case. So some steps here that I'm gonna discuss are specifically or in general applied to telephone surveys, but most of the steps actually that I'm going to talk about here today can be applied to other kind of surveys, right? Not necessarily only to telephone surveys. And as I said before, this is a part of the presentation that I'm going to have more mathematical formulae, and I'm going to try not to focus so much on that. But for those who are interested, you can take a look at that later. And if you have any questions, feel free to send me a message, send me an email. Okay. Oh, and by the way, I'm going to also, throughout the steps here, give like try to give a small examples so that like you have a little bit more of an idea on how like these things works in practice. Okay, so why do we do weights? Why do compute weights, right? So there are like a few reasons why we generally compute weights. First one is if you're working with a probability-based survey and you are working with a sample that assigns for different reasons, different selection probabilities across cases in your population, you want to account for that. You want to compensate for this unequal selection probability. So that's usually the first step in a weighting process. You should have the selection probabilities computed for your sample cases, for your respondents, and you're going to use those selection probabilities to compensate for these differences in selection probabilities through these base weights. There are also other adjustments that can be done throughout like this process. I'm going to talk about those, like especially on the telephone survey case. You're going to have things like adjustments for multiplicity, sampling frame integration if you're working with a dual frame survey, as I mentioned last week, and within household selection. Then another adjustment that you can make through weights is those cases that you don't know if they're eligible or not, right? You have to do something about those. And there's an adjustment that you can make, an adjustment for this unknown eligibility. I'm going to cover that also quite briefly. Then another reason to use weights is to try to adjust for certain non-sampling errors, right? So we all know that most surveys, you will have some level of non-response. And if respondents and non-respondents are different, you might have some non-response bias. You want to try to, and through weights, you might be able to maybe, not maybe, very likely you will not be able to completely remove that non-response bias, but you want to at least try to reduce it. There's also, especially for example in telephone surveys, as we discussed last week, there are certain coverage issues which can lead to coverage bias. We discussed last week the issues of undercoverage bias. Through weighting, again, you won't be able to completely eliminate that source of bias, but you want to try to reduce it. We're going to talk a little bit about that as well. And then finally, another reason to compute weights is sometimes, or a lot of times, we have external data about our population, distributions of our population that we would like to incorporate in your sample. And incorporating those external information can improve the precision of our survey estimates. That is, you can get smaller standard errors, smaller confidence intervals, and this kind of incorporation can also further reduce non-sampling errors like non-response and coverage. So as I said before, the basic weighting steps are usually very similar for different types of data collection, whether it's face-to-face, telephone, web, mail, mixed mode designs. And so the general scope here are going to be very similar, regardless of the mode. But today I'm going to talk about a couple of steps there that are very typical of telephone surveys. I'm going to mention those during the presentation. Okay. So here is how the general process, how we would like to see how these general steps in weighting work, right? Like this is actually more like the steps in a survey data collection process and how weighting addresses those. So you start with a sampling frame of a population of size capital N. You select a sample of size N. And if you select that sample, assigning an equal selection probability to cases, you want to compensate for that. You want to address that through weighting. So that's like the first step you're going to do. Then during data collection, some cases you will be able to determine their eligibility. Those are going to be the non-eligibility cases. But there will be cases that because you're not be able to contact anyone, for example, the household, you might not be able to determine the eligibility. Those are going to be the unknown eligibility cases. Both of these cases here are going to have some base weights, but you have to do something about this unknown eligibility cases here. So we're going to do some sort of compensation for this. Then you're going to have, whether they're eligible or unknown eligibility cases, some of those cases are going to be eligible for a survey. Some of those are going to be not eligible. The cases that are not eligible, that's fine. Like you can forget about those because they are not part of our target population. You can set them aside. You don't need to worry about them at this stage. But among the cases that are eligible, you will then have, like in most of the cases, two groups, respondents and non-respondents, right? Like I'm yet to see a survey in which you only have respondents. You have a 100% response rate, right? Like that's the dream of every survey statistician or survey methodology, right? Or maybe not. Maybe like if we have like such surveys, we lose our jobs, and like we don't want that. So anyhow, we have this problem of non-response. So here we have like these two groups: eligible respondents, eligible non-respondents, and because there might be differences between respondents and non-respondents, you can have some non-response bias. So we want to try to address that. You want to compensate for this non-response issue. There's going to be another step in weighting that we're going to do that. And finally, there might be external information from the population certain parameters or distributions that you want to incorporate in your weights. And that's what we're going to do on the very last step through a procedure that we call calibration. Okay. So starting here with a very basic example, okay? And that reflects the example that I'm going to use throughout the series of slides. Let's assume that we have a telephone survey. Okay, we selected, for example, an RDD telephone survey. For those like who were here last week, you should know or have an idea of like what is an RDD telephone survey. And let's assume that that survey was selected with a stratified random sample by region. That is, we stratified the population into like these 4 regions: West, Midwest, Northeast, and South. Like that's actually a very American example because those are the typical census regions we use here in the US. And within each one of those regions, we pretty much selected a simple random sample. So every a simple random sample of telephone numbers. Let's assume for now, okay? So every telephone number in each one of these regions have the same selection probability. Okay, but across these regions, they might have different selection probabilities, depending, for example, on what was the sample size that is selected in each region, right? So the first thing that you're going to do on weighting is to have those selection probabilities calculated for every case in your sample, right? So on this case here, those selection probabilities are very simple, right? Because we selected within each region a simple random sample, right? Like the selection probability here will just be the sample size, the number of telephone, the counts of telephone numbers that you selected on that region, divided by the total number of telephone numbers on that region, right? So assuming that we know what is that total count of telephone numbers in the region, that selection probability will just be the sample size, lowercase n sub h, divided by the population size, capital N sub h. So here we have like the different selection probabilities for each region, but all the telephone numbers, for example, all the 220 telephone numbers selected in region West have the same selection probability of 0.000008795, okay? And the same thing for the other regions. So what is the base weight, right? Like I didn't say how you compensate for that, but like the idea is very simple. We compensate for these unequal selection probabilities by computing a weight that is the inverse of that selection probability. So the base weight in general, like that will be true for any survey that you want to compute weights. The base weights will be computed as the inverse of those selection probabilities that you should have if you have a probability sample, right? That you should have like computed for every selected case in your sample, all right? By the way, and this will be done for every case literally, like respondents or non-respondents, cases that you know their eligibility and don't know eligibility. So you're gonna have a base weight for every case in your sample, regardless of their response status, regardless of their eligibility status, okay? In fact, in theory, you can even compute those base weights for every case in your population, but you won't have to do that in practice. You just need to do that for the cases that were selected in your sample. So in our case here, every telephone number selected, each one of these 220 telephone numbers selected in the region West will receive a base weight of 1 over this selection probability, which will be 113,701. No, 113,701.81. Okay, so this is going to be for the base weight for those cases in that West region. And the same thing for the other 4 regions. Okay, so even though this first step looks quite simple, right? You need to have those selection probabilities computed. And that's the part that can be tricky depending on your sample design, depending on how well you track those selection probabilities. But typically for telephone surveys, because we generally work with an RDD sample that will either be as a simple random sample or at most a stratified random sample, those selection probabilities are going to be computed in a pretty straightforward way. Okay, so that was the first step. The next step is this adjustment for unknown eligibility, right? So as I said before, there will be cases that for some reason we won't be able to determine whether that is an eligible or ineligible case. So in the telephone surveys, that's our focus today, it's typically those cases, those telephone numbers that you call, and for example, it rings, 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 and nobody answers, right? Or it goes to a voicemail, right? And even though sometimes you might be able to even say, oh yeah, the voicemail belongs to someone, sometimes your survey has certain eligibility criteria. You, for example, only want to select persons between the age of 18 to 50 years old, for example, right? Or 16 and 15 years or 49 years old if it's a fertility survey, for example, right? So even though on the cases that you say reach a voicemail and you can tell that it's someone, that telephone number, that cell phone number belongs to someone, you cannot determine whether that person falls in your eligibility criteria, right? So those cases would tend to be cases that you don't know the eligibility. But however, as I mentioned before, you will those cases still are going to have some base weight, and you have to do something about those base weights. So this unknown eligibility adjustment and the non-response adjustment they're going to talk about later will pretty much allow to allow the respondents to wait up to the full eligible population. You're going to see how in a second. And by the way, at this stage, if the ineligible cases in your sample, right, they're going to have also base weights, those ineligible cases, but those cases can be excluded now from your from this weighting procedure because they don't belong to your target population. So you don't care about those. But what I was actually mentioning here is that if for some reason, this is very rare to happen, but if you can, before the selection, exclude all the ineligible cases from your sampling frame, all the cases that are going to select in your sample, you know they're going to be eligible, and this step can be ignored. But typically, we cannot do that. Like I at least don't know, I have never worked in a survey in which we were able to exclude every ineligible case. There's always like some thing there that like makes things a little bit more complicated, that like you can't really ascertain for sure that every case in your sampling frame is eligible, especially on telephone surveys. So this is the part here on that fluxogram that we're talking about now, this unknown eligibility adjustment, and how we compute that. And so here's the mathematical formula part that like I will not go too much into the details, but at least I'm going to give a brief idea on how this adjustment works. What we're essentially going to do is those cases that you don't know their eligibility, they will have, as I mentioned before, base weights, right? Like you're going to compute even for because those cases were selected, right? Like those telephone numbers were selected. It's just that you didn't know whether the telephone number belonged to a household, an eligible household or not, right? But you're still going to have a base weight. But you don't know, right? Like whether those telephone numbers are eligible or ineligible. So if you just exclude those, you might be underestimating your population, right? Because you might be excluding a bunch of cases that would actually be eligible, even though you don't know their eligibility. If you use all of them, even though you won't be able to use them because you won't have any data collected for them, but let's assume that you want to use all of them, you will probably be overestimating your population because you're including there a bunch of cases that are very likely to be ineligible, right? So what do we do with those, with the base weights of these cases that we don't know the eligibility? So the idea essentially is to take their base weight and redistribute across the cases that you know the eligibility, respondents and non-respondents, okay, and ineligible cases as well. So the way you do that is by computing this formula here. Again, I'm not gonna focus so much, but for those more mathy and statistics savvy, the idea is to just take the sum of the base weights across everyone in the sample, whether you know or don't know the eligibility, whether the respondents and non-respondents, and divide by the sum of those base weights only across the cases that you know the eligibility. That's going to be an adjustment factor. I'm calling here A1. And you're gonna take this adjustment factor and multiply by the base weights of the cases that you know the eligibility. So like this notation here is just saying, you're gonna compute this adjustment factor this formula only for the case that you know the eligibility. For those cases that you don't know the eligibility, you're going to assign this adjustment factor equals to 0 because you're going to eliminate those, right? So what essentially doing here is just redistributing the weights of the cases that you don't know eligibility to among the cases that you know the eligibility, all right? So as an example, right, like on my previous example that I was saying before, I computed actually those sums, right? Like I took the sums of the base weights divided by each one of those 4 groups: eligible respondents, eligible non-respondents, ineligible, and unknown eligibility. So you see here how important it is to keep track of those final disposition codes, right? Here's an example on like how we use those on weighting adjustments. And this A1 factor here, I computed, you see like it's 1.4517. I computed by just taking the sum of all of this base weights across all the 4 groups divided by the sum of these first 3 groups here, which are the groups that we know their eligibility status. We know they're either eligible, respondents or non-respondents, or ineligible, right? If you do this math here, if you do this computation, you're gonna get like an adjustment factor of 1.4517. And the unknown eligibility cases are gonna have an adjustment factor equal to 0, right? So we're gonna assign a weight of 0 now. What we're essentially doing is inflating the weights of the cases that we know the eligibility status and removing from our sample, essentially assigning a weight of 0, the case where we don't know the eligibility, because we redistributed that weights among the cases that we know the eligibility status. So that is a very crude adjustment, right? Like that's an adjustment that will not do, we'll just make, and this is something that I should have said before, and you should have in mind that a very good check for your weights, like a very good data quality check, is to see if the sum of the weights sum up to your population size. On this case here, because we're talking about telephone numbers, the sum of the weights should sum up, at least at this stage, to the total number of telephones in the population, right? So what all of that adjustment is doing is, by removing the case that we don't know the eligibility, the sum of the weights are still summing up to the total number, the total count of telephone numbers in the population. Okay, if we just completely remove the unknown eligibility cases without making that redistribution, that readjustment, we would be falling short in terms of like the total count of telephone numbers in that region or country, right? So that's why we make that distribution. But it will only do that for you. It won't make any sort of like, if there are differences between cases that you don't know eligibility and eligibility in terms of like certain survey variables, that could bring you some biases in your estimates. And that sort of adjustment won't address really any source of bias. So another adjustment that you can make is a class-based adjustment, in which you're going to do exactly the same thing that we did before, but before you make that adjustment, you're going to first divide your sample into classes, and then you're going to do exactly that adjustment, right? Just redistribute the weights of the unknown eligibility cases among the cases that you know their eligibility status, but within each one of those classes. Right, so like this is what this formula is saying. So I'm not going to go too much over this formula, but I'm going to go back to the example. So what we're going to do is, on this case, because on telephone surveys, unfortunately, we don't have a lot of auxiliary information from the frame. All I have was region. I mean, our classes are going to be region, right? So that's actually a very typical weakness of telephone surveys, right? Like compared to, for example, face-to-face surveys. We typically have very little auxiliary data that we can use for this kind of like weighting adjustments. So in this case, I'm using region to form those classes. And what I'm going to do is I'm going to compute that adjustment factor, that A1 factor, within each one of those regions. So what I'm going to do is this adjustment factor here within each region is going to be the sum of the base weights across all the cases, whether they're eligible, ineligible, or unknown eligibility. So this is the total here, divided by the sum of the base weights among the cases that we know the eligibility status, whether it's eligible respondents, eligible non-respondents, or ineligible, right? So again, if you do this math here, this total divided by the sum of these 3 columns here, you're going to have this adjustment factor. By the way, I'm not sure if you can see my pen moving, so let me just use my laser point. So if you take this total here and you divide by the sum of these three groups here, you're going to have this adjustment factor for West region, and the same thing for the other three regions. Then what you're going to do, your new weight, your unknown eligibility adjusted weight, is going to be your design weight, right? So the design weight for West region was 113,701.81, and multiply by this unknown eligibility adjustment factor, 1.5385, and that's going to be now the new weight for the cases in the West region. And we're going to do the same thing for the other three regions. Okay, we're going to keep track of this example. Now, the next step is a multiplicity adjustment. So what happens, and this is very typical for telephone surveys, but it can also happen in other kind of surveys. What happens is that in telephone surveys, if a household, for example, has more than one landline number, right? Because we're sampling telephone numbers, right? If you're doing a household survey, households with more than one landline will have a higher chance of selection, a higher chance of probability of being a higher chance of selection, a higher probability of selection than households that only has, for example, one telephone number, one landline number. Same thing with cell phone numbers, by the way. Individuals that have more than one cell phone number will have a higher chance of selection than individuals that has only one cell phone number. So this is also another source of differential selection probability, and you want to address that. So first, very important thing, in order to address that, you're going to need to collect that information. You're going to need to ask to your respondents how many landline numbers they have in their households, how many cell phone numbers they own, right? And then you're going to use that information to address this multiplicity issue. And how you do that, it's very simple. Again, you're going to compute an adjustment factor for what we're going to call a multiplicity adjustment factor. And then multiplicity adjustment factor, in the case of telephone surveys, is just going to be 1 over the total number of phone lines that the respondent answer they have, all right? So very simple adjustment. What we're doing here pretty much is cases that have a higher number of telephone numbers, that they own a higher number of telephone numbers, they will have higher chances of being selected. So we're going to compensate that by giving them proportionally smaller weight, right? We're going to decrease their weight because they have a higher chance of being selected. And sometimes, by the way, depending on what is the maximum number they observe of the respondents reported in terms of telephone numbers, you will cap this this count of telephone numbers at a certain value to decrease, to control the variability of the weight. So, for example, say that someone in your sample, right, said that they have 10 telephone numbers, right? Okay, a little bit unlikely, but can happen. That sort of variation will cause you trouble later on. So sometimes what a lot of surveys do is they say anyone that responded they have, I don't know, 4 or more telephone numbers, we're just going to assume that they have 4 telephone numbers, and that's what we're going to use on this multiplicity adjustment. Okay, so that's what we did here on this example here. So again, let's go back to our West region. Now, if you go back to a couple of slides, you're going to see that now our unknown eligibility adjustment weight for the case in the West region is equal to 174,130.2. And now, depending on the number of telephone numbers, the count of telephone lines that the respondent on that region reports to you, you're going to have a different weight. So say that they have only one telephone number, great. Their multiplicity adjustment is just going to be equal to 1. If they reported that they have 2 telephone numbers, your multiplicity adjustment is going to be 1 over 2, 0.5. If they reported they have 3 telephone numbers, their multiplicity adjustment is going to be 1 over 3, 0.3333. Now, if they reported to have 4 or more, and this is where we're going to put that cap on the number of telephone numbers, their multiplicity adjustment is going to be 1 over 4 or 0.25. So what we're going to do with this adjustment factor, I actually didn't say, we're just going to take our previous base weight, our unknown eligibility adjusted base weight, and multiply by this multiplicity adjustment factor. So on the West region, these are going to be the new design, the new adjustment, multiplicity adjusted weights depending on how many phone lines the respondent reported they have. Okay. So that's the multiplicity adjustment, pretty straightforward. Now, the next thing is frame integration. And this is mostly due if you're working with dual frame designs. And this is like very typical on telephone surveys, right? So going back from last week, for those who didn't attend it or don't remember, dual frame designs are designs in which you're selecting both landline numbers, so from a landline frame, and cell phone numbers from cell phone frame. Now, what's the problem? The problem here is that individuals that only have landline or individuals that only have cell phones are going to have a smaller chance of selection than those individuals that have both landline and cell phones, right? What we call dual users. Last week, we covered a couple of ways to address this issue, right? You can either just let it happen, is what we call like overlapping design, and you're going to address that through weighting, and that's what we're going to discuss next. Or if you want to avoid having to deal with this weighting complication, you can use a screening design, which is a little bit less efficiently in terms of like data collection field, because on this design here, you're going to be screening out from one of the two frames, from one of the two samples, the dual users, right? So in this case here, in this example here, we're only gonna screen in the survey dual users that comes from the landline sample. Any dual user that comes from the cell phone sample, you're gonna screen out of your survey, right? Not very efficient in terms of production, right? So a lot of designs, a lot of surveys prefer this overlapping design, but if you're adopting this overlapping design, you need to address through frame integration. You need to address that those unequal selection probabilities here through frame integration. So first thing, you need to collect the information about which domain your respondent fall. And by domain, I mean whether they are landline only, cell phone only, or they are dual users. They have both cell phones and landlines. So for example, the National Health Interview Survey here in the US uses like these 3 questions here to determine like this domain membership, right? Like if there is at least one telephone inside your home that is currently working, it's not a cell phone. If the respondent or anyone in their family have a working cell phone, and how many working cell phones do you and other people in your family have? So with these 3 questions, you can kind of like assign which domain the respondent is, whether they are landline only, cell phone only, or dual user. Now, this frame integration have different approaches in the literature. I'm going to just talk about one of them, but there are 2 that are very dominant. There is one, this composite estimator, which is one that's going to use like a parameter to try to compensate for this dual users in a way. Again, not gonna talk about that, but for those who are interested, I can point out to some references. And there's a single frame estimator, which is the one that I'm going to address. So the idea of the single frame estimator is to use just like a very simple probability property, which is the probability of belonging to, I'm going to translate what this probability property means for those who are not like mathy or statistics savvy. The probability of belonging to both landline and cell phone frame, that is of being like a dual user, is equal to, or being selected, I should say, or being selected either through a landline or a cell phone frame, is the probability of being selected through the landline frame, right, through a landline telephone, plus the probability of being selected through a cell phone frame, a cell phone number, minus the probability of being selected on both of the 2 samples at the same time, right? And here we're gonna assume that this probability of being selected on both at the same time is just a product, is just the multiplication of the probability of being selected through the cell phone frame and the probability of being selected through the landline frame, right? So in a dual frame telephone sample, the design weight is going to be given by, again, 1 over that selection probability, right? So the inverse of that selection probability. So on this case, it's going to be 1 over the probability of being selected through the landline sample, the landline frame. I'm going to denote here this probability of selection of the landline sample by pi sub L, if the respondent is a landline only respondent. It's going to be 1 over the probability of being selected on the cell phone sample or 1 over pi sub c. This pi sub c is the probability of of selection in the cell phone frame, if that case is cell only. And it's going to be 1 over the probability of being selected in the landline frame plus the probability of being selected in the cell phone frame minus the product, the multiplication of those two probabilities if your respondent has both a landline and a cell phone. That is, they are on that dual user domain, right? So this is essentially how we deal with frame integration in dual frames using the same single frame estimator approach. So here is just like a way, a way how we would compute those selection probabilities, right? Like assuming that you have a synchronous sample in each one of the landline and cell phone frame, the selection probability is just going to be the sample count on that frame divided by the population count, the number of telephone numbers on that frame, right? Like, so that those are going to be how you select those, how you compute those selection probabilities. And again, depending on the domain that your respondent fall, whether they're landline only, cell only, or dual, these are going to be, these first two lines are their selection probabilities, and their base weight are given by this by these quantities, which is exactly equal to the previous slides. So just populating with some counts using my example here, and this is, I think, is again in that West region, for example, right? Like, so we have, I think, 220 cases selected. Imagine, let's assume that 120 of those telephone numbers were from the landline frame, 100 came from the cell phone frame, and those are the counts of landline and cell phone numbers in each one of those frames. So you would compute those selection probabilities. So this is the selection probability of being selected on the cell phone or the landline frame, and this is the selection probability of being selected in the cell phone frame. And then the weight will depend on whether your respondent is landline only. If it's landline only, it's just going to be 1 over that selection probability of being selected in the landline. So that will be their base weight, 125,072. If they're cell only, their selection probability is just going to be this cell sample selection probability, and you're going to take the inverse of that as a base weight. And if they're dual frame, you're gonna have to do that little math there, which is going to be 1 over the probability of selection in the landline plus the probability of selection of cell phone minus the product of the two. And like this is what you will get if you do that, or this would be the probability, and you would take like the inverse of that probability. Okay. All right. So how we're doing on time here? Ooh. Okay, not very good, huh? I need to go a little bit faster. So within household selection is something that not only telephone surveys does, other kind of surveys do as well, right? So face-to-face surveys. Sometimes, or a lot of times, we don't take everyone in the household. We select a subsample, usually one respondent per household. And again, because households vary in size, selecting one person in a household of 5 people, we will assign a different selection probability than selecting one person in a house with only 2 people, right? Like the individuals living in the 2 different households will have different selection probabilities. And you need to address that again. So one way to address that is by just multiplying your base weight by the number of members in that household, right? So again, going back to our West region example, with only, let's assume that we only have one telephone number for a certain household. Depending on the number of adults in that household, these base weights are going to be multiplied by this number here. So in a household with only one adult, you're going to just take that base weight of 174,930.2 and multiply by 1. So that's the base weight for that respondent in that household with only one adult. If that the household has 2 adults, you're going to multiply that base weight by 2, right? Because compared to that household with only one adult, though that household with 2 adults have half of the chance of being selected because they're selecting only 1 over 2. The same idea with a household with 3, 4, and again, a lot of times we cap the number of household members at a certain value, on this case, like here 5, to avoid like a lot of like variability on the weights. All right, so here's the good part of the interesting part that probably a lot of you are thinking. So non-response weighting, right? So a lot of the times, not a lot of times, most of the times, respondents and non-respondents in your survey will differ. And in most of the surveys, if not all of the surveys, you're going to have some level of non-response. And if respondents and non-respondents differ, you have most likely non-response bias. So we want to use some sort of like weighting to address this non-response bias to try to at least reduce it. As I said before, we probably will never going to be able to completely eliminate it. So I just want to call you for the fact that the following. So imagine that the probability of selecting someone in the sample is given by this parameter, pi I, right? Like, so that's what we used to calculate those base weights. We took the inverse of those selection probabilities, pi I, to address this different differential selection probabilities. Now, you can think of the same thing now for the probability of response. Sometimes we call it response propensity, right? Let's call that probability of response or response propensity by phi I, okay? Okay, so on the fluxogram, this is where we are. But what I want to say is on the base weight, in order to address those differential selection probabilities, what we did was we took the inverse of those selection probabilities, right? We took 1 over those pi i's. So I guess that one very intuitive thing to do is let's take the inverse of these response propensities or responding probabilities to adjust for non-response weights, right? So that then we would have as a final weight the inverse of the product of the selection probabilities pi I and the responding probabilities phi I. Okay. Now the issue there is that unlike the selection probabilities, in a probability based sample, the response probabilities, the response propensities, we don't know that, like, because that doesn't we don't have control over who responds or not. We have control in the sense like we know who we select in the sample and who we don't, but we don't have any control over who respond or serve and who don't respond. Like that is almost up to the respondent, right? So then the idea here is to estimate those responding probabilities, those phi i's, estimate somehow. I'm going to show how to estimate and use the inverse or somehow the inverse of those responding probabilities as adjustment factors. So how do we estimate that? There are a few ways to estimate the response propensities. One is to just use the overall response rate of the survey as an estimate of that response propensity, and then use the inverse of that response rate as an adjustment factor. The issue there is that this assumes a very strong mechanism. It assumes that missingness is completely at random. It assumes actually that respondents and non-respondents are not different, which is not the case in most of the cases, right? So this is not going to do anything for you in terms of adjusting for non-response bias. So another way is to use auxiliary variable that you might have from your frame or from your sample to estimate those response propensities. So let's assume that we do have a set of auxiliary variables, x and a vector xi here. But one very important thing is that you need to have those variables available for both respondents and non-respondents, right? So this is a very important but also hard condition, I know, because most of the times non-respondents are non-respondents and we don't have any information from those. But if you do have at least some auxiliary information, we're going to use those. And the idea will be to form classes, again, similar to the unknown eligibility adjustment. What we're going to do is we're going to form classes of sample cases, right, based on those auxiliary information, and we're going to use the inverse of the response rate of each one of those classes as an adjustment factor. And that response rate can be either an unweighted response rate, which is just going to be the number of eligible respondents divided by the total number of eligible respondents and non-respondents. That would be like the unweighted response rate, and you're going to use the inverse of that. Or you can use a weighted response rate, which is going to use the sum of the design weights. Again, I'm not going to go over this formula here, but the idea is to just use the design weights to weight your response rate. But essentially, you're going to form those classes and then take the inverse of the response rate as an adjustment factor and use that adjustment factor on the computation of your weight multiplied by your design weight to get a non-response adjustment factor. So on our going back to our example, what we would do is, unfortunately, again, on telephone service, we don't have a lot of auxiliary information for both for respondents and non-respondents. So on this case here, we're once again going to use region. That's all we had. And what we would do is we would compute, like for each one of these regions, we'd compute the response rate and take the inverse of the response rate. So here's the inverse of the response rate for each one of these regions and use that as an adjustment factor. And as long as there are differences across region between respondents and non-respondents, you're going to be adjusting for non-response bias in that. Are you going to be able to completely remove non-response bias? Very likely not. But you're going to be able to at least somehow reduce a little bit that non-response bias using this approach. There is another approach here. I'm not going to talk so much because it involves a lot more statistics, but for those who are more statistics savvy, you probably know that you can use propensity score adjustments, which will pretty much model the response indicator using some sort of like binary regression model, like a logistic regression, probit, or complementary log-log model. And using that logistic regression, if you have like a more, and this is very helpful if you have more auxiliary information from respondents and non-respondents rather than just categorical variables. You're gonna estimate the response propensity using the coefficients of that model, and then if you're using a logistic regression model, right? Like you're going to use, on this case here, the inverse of the logit to estimate those response propensities. And then there are different ways to use those estimated response propensities. You can just use the direct inverse of those estimated response propensities as an adjustment factor. However, this puts a lot of dependency on the response propensity model. If you do have a good response propensity model, that's great. If you don't, you're gonna have like some issues. So one way to avoid that is to use this propensity stratification approach, in which you're not gonna use those response propensities directly in the adjustment. You're going to use those to create groups of respondents based on the response propensities. You're going to order your respondents according to those estimated response propensities, form classes, and then use the inverse of the response rate or the inverse of the average response propensity in each one of those classes as an adjustment. I know I went very quickly here, but like if you look at this reference and like look a little bit with more time onto the slides, hopefully you can understand. If not, like I'm available to answer any questions. And finally, calibration. This is what I was mentioning before, and this is a very powerful way to address non-response bias, address coverage bias in the lack of auxiliary variable available for both respondents and non-respondents. Why that's the case? Because on this case here, all you need is auxiliary information collected from your respondents. And that's great because your respondents might be able to provide you with that information, right? So usually those, especially on household surveys, they tend to be like demographic variables like age, race, ethnicity, gender, income, things like that. However, one thing that you need for this kind of adjustment is you also need that same auxiliary information from your population, whether it is at the individual population unit, that's usually not typically the case, or in an aggregate form, like the distribution of the population. So for example, if we're using age, what's the distribution in the population of males and females? What's the percentage, 50-50? The distribution of gender, not gender, age, right, across age groups. If you had that information, you can use this approach, this calibration, to adjust your weights so that your sample distribution reflect that population distribution. And by doing that, you might be able to not only reduce non-response and coverage biases, but you can also improve the precision of your estimates. You can decrease the standard errors or the confidence intervals of your estimates. So yeah, that's all the things that I've already said. There are different ways to do this calibration. I'm going to talk about two of those very briefly. One is post-certification. Probably a lot of you have heard about this, right? Post-certification. What do we do here? Here in post-certification, you typically have a few auxiliary variables, usually categorical variables, like age group, gender, and ethnicity. And you generally cross-classify all the categories of those auxiliary variables to form cells, to form groups. And if you need to have now the population distribution of that cross-classification to be able to make that adjustment. Now, one very important thing, if you have to take anything away from this presentation, is in order to have the best adjustments on this calibration adjustment, or for example, post-certification here, it's very important that the auxiliary variables that you use on this adjustment are very well correlated to your survey variables. If that happens, the potential to reduce non-sampling errors like non-response and coverage, and to improve the precision of your estimates increase a lot. Okay, so that's very important. So how we do post-certification? So assume, for example, that we have two variables only: gender and education. Gender, male, female, education with these four categories here. You're going to cross-classify them. You're going to create 8 groups. You're going to classify gender by education, right? So 2 gender by 4 education. You're going to have 8 classes. And you're gonna use the population distribution of these 4 classes to adjust your weights so that your sample distribution on those 8 groups, sorry, matches the population distribution. As I said before, it's important. Okay, no, I said before. Like using many important auxiliary variables can reduce bias. However, if you use a lot of variables, you can end up in a case in which you have weighting cells or weighting classes that either have very small number of respondents, what we call sparse cells, or are even empty. And this can result unstable estimates of the populations, and it can add variability to other weights, which we want to avoid. And we're going to talk briefly about what you do in those kind of situations. So the post-certification adjustment here is computed very simply. Like in each class, you're just going to take that population count or population distribution, then divide by the estimate of that population count using the base weights, right? So it's going to be the sum of the base weights on that class. And that's going to be the post-certification adjustment. I'm going to give an example here. Imagine that this is the population distribution on this column here for this gender by age distribution, right? And you took your sample and you sum up the base weights for each one of these groups, of respondents on these groups. So the post-certification adjustment is very simple. It's just going to take this population count that probably is going to come from census data or from a previously higher quality survey data, and divide, or a population projection, and divide by this this estimate that you get from your sample by summing the base weights among the respondents in that group. And this is going to be your post-certification adjustment. We're going to multiply that post-certification adjustment to those base weights to get a final calibrated weight. So finally, raking, the last thing I'm going to talk today. Raking is another very popular form. It's actually even sometimes more popular than post-certification, because the idea of raking is very similar to the post-certification. You're going to have variables, auxiliary variables, they want to match your sample to population distribution. But instead of cross-classifying all the categories of if you have 2 or more variables of those variables, you're going to only use the marginals of the variables. So for example, you're only going to use the age distribution. You're only going to use the gender distribution to adjust your sample distribution. You're not going to use the age by gender distribution. This is actually very interesting because a lot of times we don't have those cross classifications available through census or other population projection data. And it also decreases the issue of those small cells or empty cells, weighting cells, right? So what we would do here is we would first adjust the weight by gender, for example, right? And the idea is very similar to the post-certification, right? Like it's going to be just the population count of that gender category divided by the estimate of the population count. Then you're gonna make that adjustment, and you're gonna use now this gender adjusted weights to adjust for age, right? So you're gonna take the population counts of age, and now the sum of the weights adjusted by gender here to compute this new adjustment. However, when you do this, now your gender distribution are gonna be slightly off. So you're gonna repeat this process in an iterative process here until the distribution of these two margins converge. Okay, so that's essentially the idea. There's a lot of software that actually implements both of these approaches. I can point out if you need at some references for that. Finally, there's weight trimming. I'm going to talk a lot about that, but a lot of the times after you go through this whole process, there are going to be some weights, for some cases with weights that are very large or sometimes very small. And this can cause us problems in terms of like sampling variance, in terms of the precision of your estimates. There is this measure called unequal weighting effect by Kish that evaluate the impact of the weight variability, which you can use to guide that. So this essentially is going to give you how much inflation in your sampling variance you are having by the variability of the weights. And you want to have this you want to have this under control, right? Like, so say that this unequal weighting effect is equal to 2. That's pretty much saying that you're doubling your sampling variance because of the variability of the weights. So one way to address that is by trimming the weights. Like trimming, essentially the idea is taking those very large weights and putting a cap on them. You're gonna, okay, so if I have a weight equal to 500,000, I don't want that. I'm going to trim that weight to up to, I don't know, 100,000 or something like that, right? There are different ways to do trimming. There's a vast literature as well. I'm more than happy to point out to some references, but I just wanted to mention that like this is another very important and one of the final steps, or if not the final step in weighting. So some of the references here, for those who are very interested in learning more about weighting and like want very good references, I have these last two here, these last two books, they're two books by pretty much the same authors. They address very well, like this first one here, Practical Tools for Designing and Weighting Survey Samples, have a very good 2 or 3 chapters only talking about weighting. And I think they use R, if I remember correctly. And this last book here that was recently published in 2018, same authors pretty much, is a book only about weighting, but here they use Stata. So for Stata users out there, like if you like Stata, you can take a look at this book. For our users or like more general users, like because this one here goes through more like general theory, you can take a look at this book. Okay, and a lot of the notes, by the way, were based on these 2 books here today. All right, well, so thank you. I know that I went again way over time. We don't have a lot of time, I guess, for questions, but it doesn't look like we have a lot of questions in the chat box here today. So
not many questions today, Raphael, but very good questions, I must say. So we have only 12 minutes or so for the questions and answers. So let me get straight into them. And I will ask you to please keep your responses brief, as brief as possible, so then we can include as many questions as possible.
Yeah.
The first question, can selection, and I will extend this question, which came from one of our participants, to something else. Can selection probabilities be determined for non-random samples? And let's extend it to say, if there has been no selection probabilities as a purposive sample, can we actually weight the sample? Or can we actually calibrate? Can we actually come up with something that will enable us to say, I have made this sample representative by doing calibration, by doing weighting, etc. The second question, more of a comment, is that the AA-POR standard recodes, standard response rates, the chart that you showed, the list that you showed, may not be covering all types of other types of new phone surveys, like the ones that we are now working on, several agencies, which are using household survey frames and using phones to reach out to the households. Those response rates may be in light of some new applications. We might want to revisit those codes, is one comment. Another comment is in countries where with low coverage of phones, how can we adjust the weights for coverage bias? And finally, a question that I got even before the webinar is, what is an acceptable response rate for a telephone survey? And then remember last week there was a comment on, there was a question on what are the typical response rates for telephone surveys. And let me rephrase the question a little bit. When should I start to get worried? When, at what level of response rates should I start to get worried about my representation of the population?
Okay, so let's try to go by parts here. First question, very good question about like base weights or weights in general for non-probability samples, right? So there's actually more recently been some developments of methods to compute pseudo weights for non-probability samples. I can include actually, I don't have here on the list of references, but I can include there's at least 2 or 3 papers. But essentially the idea is that you're gonna have to use some models to try to at least compute some pseudo selection probability for those cases. In general, those methods have to use some sort of like benchmark survey. There is like a probability based survey in order for you to do that sort of thing. And there are another couple of approaches, but this is just to talk about like selection probabilities, which obviously you don't have on non-probability samples, right? Like, you know, because they're non-probability samples, by definition, they don't have selection probabilities. Now, that doesn't mean that you cannot compute weights using calibration methods like post-verification or raking. You can still do that. It's just that you're not going to have those previous steps that I talked before. Like, you're not going to have a design weight. You're not going to have most likely a non-response adjustment weight, because like in non-probability samples, it's very hard to distinguish what is like a respondent and non-respondent in general. So yeah, I can point out to a couple of references that I can include on the presentation or on the set of references that some develops on that. Second question, what was the second question again, Attila, that you were mentioning?
The AA-POR standard response code that you showed in one of your screens. Saying that they might not be applicable to some new types of surveys, like the ones which are using household survey frames and calling households by phone. The response codes that we might, and eligibility there might be quite different from what is on the AA-POR website.
Oh, okay, yeah, okay, that's a good point. So I mean, it's obviously that doesn't cover all the possibilities in surveys, right? Like in modes of data collection, what they have there. You will probably need to adapt, right? Like what they have for telephone surveys to your case, or what they have there, like sometimes on face-to-face. Like, you're probably gonna have to find like a good what you say, mix between the two. But one important thing, though, to keep in mind is that you want to track the, if you're doing this kind of model, in the sense of like you're you're using telephone numbers from a previously selected household face-to-face survey, you want to track non-response on both levels. The non-response from the face-to-face, right? Like, I want to account for that, and then the non-response on the telephone survey, right? And so you might have to use both disposition schemes to address that, and like having response rates at like both levels. Then the third question was about acceptable response rates, and was that what it was?
That was one of the questions, yes. When do you get worried? When at what level of response rates do you start to get worried about your representativity?
Yeah, so that's the part that I'm going to try to answer by not answering the question. Because the thing is, right, like, of course, that as you might have seen, did I show that last week? Maybe I didn't. But there is a relationship between response rates and non-response bias, right? Like, obviously that, like, the smaller the response rate, the larger the non-response bias tend to be, or at least the upper bound of the non-response bias tend to be. But there is also another, similar to the coverage bias. I think that's what I was mentioning. That I was trying to remember yesterday from last week. Similar to the coverage bias, that is a function of both the coverage rate and the differences between the covered and uncovered population. The same thing is with the non-response bias. Non-response bias is a function of both the response rate. So again, higher response rates in general lower non-response bias, but it's also a function on the difference between respondents and non-respondents. So there are certain surveys that even with a very low response rate, because there's not a lot of differences between respondents and non-respondents, you might still have, like, not very large levels of non-response bias. So it again will depend from survey to survey. I can tell you this: here in the US, and like answering the question, like, what is the typical response rate for telephone surveys? Here in the US, most telephone surveys have response rates, single-digit response rates. So typically, like, lower than 10%. On average, I would say between 5 to 7, 8% response rate. Now, these calculations are a little bit tricky, because a lot of a lot of the organizations that compute response rates make some assumptions about those cases that we don't know whether they were eligible or not, right? So some of these response rates calculations are very conservative, and they assume that all of those cases are eligible cases, which tend to drop your response rate considerably, right? So it's a hard question to answer, just because, like, we have a lot of evidence over the past 10, 20 years that even though, like, these response rates have been, like, dropped considerably, and, like, over the past 10 years, they tend to have been, like, on single digits for a lot of surveys, especially things like election polls and things like that here in the US. We haven't really seen, like, a lot of bias. And I mean, that might be because some of the weighting adjustments we're using are considerably powerful, and, like, we're being able to reduce that. But it could also be because even though response rates are so low, the differences between those who answer the survey and those who don't are not that large that would produce a large amount of bias. So unfortunately, I don't have, like, and, like, that's, you probably can ask the same question to most people in the field, and at least the honest ones are gonna answer that. Like, we don't have, like, a good rule of thumb to say, hey, if a response rate is below this this value, like, you should be worried about, because we know that non-response bias is not only a function of response rates. It also depends on these differences between respondents and non-respondents, and it could happen both ways, right? Like, if you go back to my slides, like, last week, where I showed those 4 scenarios of coverage bias, right? Like, high coverage rate, low coverage rate, low difference between coverage and uncovered, high difference between covered and uncovered. You can do the same thing with response rate, with non-response bias, right? Like, even very high response rate surveys can have large non-response bias compared to low response rate surveys. Why? Because maybe those high response rate surveys might have very large differences between respondents and non-respondents, and very low response rate surveys might have very small differences between respondents and respondents. So again, very hard question. Like, it would depend from case to case, survey to survey, population to population.
Thank you, Raphael. There was a question on countries with low coverage of phones. How can we adjust coverage bias? And it was extended by another colleague to refer to a case when no accurate data on phone ownership actually exists in the country.
So
how do we deal with those situations?
Okay, that's a good question. So let me first address the first one. That's tricky because right? Like if you have very low coverage rate, right? Like as I was saying before, you might have considerably large coverage bias there if the differences between the covered population and covered population are considerably substantial. And the only way to really address that through weighting, at least, okay, through weighting is, or the most straightforward way is through calibration, right? But in order for you to have a good adjustment there in the calibration with post-certification or raking or any sort of calibration method, you're going to need to use auxiliary variables, right? Like the variables they're going to use on those calibration methods have to be very predictive of your survey variables. They have to be very well correlated with your survey variables. If they're very weakly correlated, you're not going to be able to address that coverage bias very well. And unfortunately, in social surveys, at least, that tends to be the case. We don't have like a lot of very powerful, very well correlated auxiliary data to the survey variables. But the extent to which you can obtain and collect those auxiliary variables that are powerful predictors of your survey variables, you might be able to reduce that coverage bias. Well, another property actually you should have is those auxiliary variables should also be somehow correlated to the fact on whether people are or not covered. In this case, have or not have phones. So they have to have this two-way correlation with their survey variables and correlation also to phone penetration. And the last question about phone ownership, accurate data about phone ownership. It's a good question. The thing is that a lot of surveys do use phone ownership as one of the dimensions of calibration. And if you do use that, like you would need that sort of data. However, you don't need that. A lot of surveys that I know don't add that a dimension on calibration. And for things like dual frame integration or even like base weights, you don't really need the distribution of phone ownership on the population. Or what you need is what is the count of possible numbers on each frame. And I know that this can be also another source of lack of information there. But as long as you're using RDD, you can have at least a projection of that number of landlines and cell phone numbers. So you don't need necessarily for those kind of adjustments that we're talking here today, phone ownership population distribution.
Thanks, Raphael. We have run out of time. I just want to end with reading what one of our colleagues have just put in the chat box, which is, you can read it too. I have to drop off for the next call. Thanks very much for the session. I learned a lot, including that I would probably either need to hire a statistician to do this kind of work or just go with some very blunt and unweighted data analysis, probably. So thank you very much.
Hiring a statistician.
Yeah, thank you very much, Raphael, for this great webinar. And thanks everyone for their participation and for the really great questions and comments. I'm afraid we didn't get to cover all the questions, but the communication lines are open. Please reach out to us for any questions that you might have on this topic. And just to say that next week's webinar, everyone, will be on remote sensing data by Paul Aplin from the Edge Hill University. Please stay healthy and safe, and see you next week at the same time. Bye.
Thank you, everyone. Bye-bye.